Welcome to week 7. This week we are going to be switching gears again and we're going to start talking about linear algebra and vectors. This is also what we are going to be talking about next week. Now, when I say linear algebra, what I really mean is matrices. So what are some contexts in which matrices are useful in physics? Well, one example, if you've already taken the quantum mechanics course, you probably know, is that we represent spin in quantum mechanics using matrices. Chapter 6 in your textbook introduces linear algebra by talking about the three-spring problem, which is where if you have three springs and two masses, and you want to calculate the vibrations that happen, you use matrices to solve these differential equations. And we'll come back to that one next week. The example we're going to be talking about this week relates to optics. So when you're working with optics, you need to model what light rays do. So one way you can model light rays is, say this is an example of a ray, and say this is your 0 position. So you can represent your ray by where it is and what the slope of this line is. And you represent that as a column matrix, which also looks like a vector. And you can use matrices to represent different changes in an optical system. Like if it's just propagating in free space, or it goes through a lens, or it hits a mirror, you can write different matrices that helps you model the situation. And we're going to come back to exactly how we do that after we cover some matrix basics. Okay, so first we need to cover exactly how we talk about matrices. We talk about their size by saying an m by n matrix. M is the number of rows, and n is the number of columns. For example, this is a 2 by 3 matrix. This is a 2 by 1 matrix. And this is a special case. It's also called a column matrix. Okay, let's talk about how we add matrices. And addition and subtraction, you know, are pretty similar. Subtraction just requires using a negative sign. So when you're doing addition, you have to make sure that your matrices are the same size. For example, you couldn't add these two matrices together because they're different sizes. So I'll just show you a simple example with some 2 by 2 matrices. Okay, and I'm guessing you can figure out how to add matrices together. All you do is add individual elements together. So 2 plus 1 is 3. 4 plus 3 is 7. 3 plus 3 is 6. 1 plus 5 is 6. So both these matrices have to be the same size. Your answer is the same size. And also notice that here I use brackets and down here I use large parentheses. Either one is correct when you're writing. It doesn't matter what you decide to do. And sometimes I just flip back and forth because I'm not thinking about it. Okay, just to get you warmed up, I'll give you a few addition examples to do yourself. Okay, so as always, pause the video and try it out before you press play again. So these are pretty straightforward. So a lot of times matrix operations can get pretty tedious. They're not difficult, but because there's a lot of things to keep track of, it's easy to make a mistake here and there, especially when you have signs, negative signs to pay attention to. So just try to be careful. Okay, now let's talk about matrix multiplication. So if you're multiplying by a scalar, and I mean just a regular old number, it's really simple. So if I just want to multiply this matrix 1, 2, 3, 4 times 4, you just multiply every single element of this matrix by 4. That's easy. Alright, but let's say you want to multiply two matrices together. Okay, let's look at an example. And again, it's really not that difficult, but it is tedious. So the first thing you have to check when you do matrix multiplication is you have to make sure that the sizes of the matrices are going to work out. So when you're adding, they have to be the same size. That is not the case when you're multiplying matrices. Let's write out the sizes of these matrices to see what the rules are. So this one's a 2 by 3 matrix. And this one's a 3 by 2 matrix. When you're multiplying matrices, the number of columns of the first matrix has to be the same as the number of rows of the second matrix. These two numbers have to be the same for multiplication to be possible. So you want to check that first before you ever attempt a multiplication. And then the size of the matrix that you're going to end up with is the number of rows of the first one times the number of columns of the second one, in which case, in this particular case, they're the same. So the reason that is because when you do matrix multiplication, you multiply the first row times the first column to get the entry that goes in the first row and the first column, and so forth. But let's look at what that looks like. So to get the first row in the first column, we take 2 times 5 plus 1 times 3 plus 2 times 1. To get the entry that goes in the second row and first column, we multiply the second row times the first column. So that's 3 times 5 plus 2 times 3 plus 3 times 1. Then we do the first row and the second column. Then we do the second row and the second column. This takes a little bit of getting used to, and it is tedious, but you do have to be careful that you don't make any mistakes. Okay, let me know if that makes sense. I'll give you a few to try out. And remember, the first thing you want to do before you multiply is make sure that the sizes are going to work out. Okay, pause the video and try these out. Okay, this first one, we have a 3 by 3 and a 3 by 1. So our resulting matrix is going to be a 3 by 1. And it works out because this 3 equals this 3. So we get 4 times 3 is 12, plus 1 times 8 is 8, plus 2 times 2 is 4. We get 3 times 1 is 3, plus 5 times 8 is 40, plus 3 times 2 is 6. We get 0 times 3 is 1, plus 1 times 8 is 8, plus 6 times 2 is 12. So we get, alright, next one. So square matrices, you can always multiply by square matrices of the same size. So this one's going to get you a 2 by 2. So we have 4 plus 12, 5 plus 6, 8 plus 6, 10 plus 3. So this gives us, okay. Last one. Well, this is a 3 by 2. And so is this. These numbers don't match, so you can't actually do this multiplication. Alright, and one final note on matrix multiplication is that, okay, so if you have one matrix A and another matrix B, if you flip the order of multiplication, it's not going to give you the same answer. So it's not like regular multiplication. And you can kind of see that if you look at this one, because if you try to multiply this matrix times this matrix in the other order, the sizes wouldn't work out and the multiplication wouldn't even be possible. Okay, but say if you wanted to multiply 3 matrices together, you could do it. You could do A times B and then multiply times C, or you could do b times c and then multiply a times b times c. So it's associative, but it's not commutative. All right, let me know if you have any questions. Okay, now that we know some matrix basics, let's go back and look at optics again. And what we're working with we call ray matrices. I like to talk about this example because I did my PhD working in a laser lab, so I always enjoy doing applications to optics. Okay, so remember I said that we can represent a ray as a column matrix, where the first number represents the position and the second number represents the slope of that ray. So let's draw a picture. So here's our ray. Let's say our 0 position is down here. So say our array starts over here. We'll call this location 1 or plane 1. And so the height of the ray at this point, we're just going to call R1. It has some angle right here that's related to the slope, R1 prime. Let's extend our array a little bit. Now let's start with the basic case of we want to see what happens when a ray travels through free space. It's the simplest example we could look at. Now when I say a ray travels through free space, that's the same thing as when I say a ray propagates through free space. It's just fancy words that means something pretty simple. So let's say our ray travels through free space to location 2. And we'll call this distance here d. Now what we want to figure out is how we can represent the ray at location 2. So we need to figure out how high the ray is here. Well, what position it's at. So the angle and the slope are going to be the same. We have to do a little bit of geometry to figure out what this height is here. I'm just going to call this height here y. What we are actually looking for is this height, R2, and R2 is R1 plus y. So we need to figure out what y is. Well, we can do a little bit of geometry. So we know that the tangent of theta 1 equals y over d. Well, y over d, that's rise over run. That's the slope. So this is actually the same thing as r1 prime or r2 prime. And though our first instinct is to look at trig functions, when you're talking about slope, you don't even really need them. What really matters is the second part where we found that y over d is equal to the slope. We already have the slope, so we don't actually have to worry about the angle. So we get that y equals r1 prime times d. So r2 equals r1 plus r1 prime d. We already wrote down that r2 prime does not depend on r1, but it is the same as r1 prime. This can be rewritten as a matrix equation. And I'm running out of room, so I'm going to copy this over on the next page and we'll look at it some more. Okay, so this is a system of equations, and linear algebra is very useful for any system of equations. So let's rewrite this in matrix form. See, when we multiply this out, this 1 will get multiplied times the r1, that gives us this term. This d will get multiplied times the r1 prime, this term, and that equals r2. Next row, 0 gets multiplied times r1, 1 gets multiplied times r1 prime. That gives us r2 prime. So I hope you can see that this really works out. In general, this works. So when we're talking about traveling through free space, this is the matrix you use. You just put in this d here as the distance it traveled, and this is your propagation through free space matrix. Another example of a useful matrix is the one for a lens. So that one looks like this. And since we're working with a real physical situation, you do have to watch your units. So here we have 1 over the focal length down here. So let's do an example. Let's say we start out with a ray at position 5 millimeters with a slope 0.1. So when the slope is 0.1, which actually is about 6 degrees, we want to see how we can represent this ray after it travels through a lens of focal length 100 millimeters. Okay, so I'm plugging in my focal length. Then I need to represent the original ray, so that's at 5 millimeters with a slope of 0.1. Okay, so if you multiply this out, you get 5 millimeters and 0.05 for your slope. Okay, so the propagation in free space matrix, what that does is it changes position but not slope. But when you do a lens, it keeps the position but changes the slope. Alright, I'm going to give you a couple situations in ray optics to work out for yourself. So these two questions are related. This first one, you have your original ray and it passes through empty space. After you figure that answer, that'll be your starting point for the ray that goes through a lens. Alright, pause the video and try it out. So we're passing through 30 millimeters of free space, and our original ray is at 10 millimeters and 0.2. Alright, if you work that out, you will get 16 millimeters and 0.2. And let me know if in the problem solving discussion if you want me to show the details for this. And remember, make sure your units are working out. It helps you check if your math works out correctly. Okay, second one, we'll call our answers to that one R3 and R3 prime. Now we're passing through a lens, and our starting point for this one is our answer to number 1. So if you work that out, so our first one, we end up with a ray at 16 millimeters and a slope of 0.2. So the position changed, but the slope didn't, as expected. The second one, we end up with a ray at 16 millimeters and the slope is 0.12. So now the position stayed the same, but the slope changed. And I hope this makes the abstract business of doing matrix multiplication a little bit more concrete for you. You can see how it works out with units and how it maps to a system of equations. Alright, so there's one more basic about matrices I want to cover before we move on to talking about vectors, and that is determinants. And we'll see why these are useful when we're multiplying vectors. So when you write a determinant, if your matrix is A, you write it like this. So we have straight bars, they're not parentheses, they're not brackets, they're straight bars. And we're only going to do this when we have square matrices. So to take a determinant, there's two ways to do this. I'm going to show you my favorite way to do it. So you take this number here, your 1, and you multiply it times this minus this. So 1 times 6 minus 1 times 2. Then you subtract the 2, and you do 0 times 6 minus 2 times 3. Then you add 5 and multiply times 0 times 1 minus 1 times 3. Okay. So you take your number at the top of your first column, then you look at the other two columns and do a zigzag. Then you subtract the top of the second column and do a zigzag of the columns that aren't in column number 2. Then you start at the top of the column with a 5 here, and then you zigzag over here. So when you work all that out, you end up with 4 plus 12 minus 15 equals 1. Okay, I showed you the hard one first. That is a 3 by 3 matrix. Let's say we're just doing a 2 by 2 matrix. This will be faster. This one you just go 7 times 4 is 28, minus 2 times 3 is 6, so you get 22. Okay, another tedious thing to keep track of. But we'll get to at least one thing it's useful for in a minute. I'm going to give you just 2 of them to try for yourself, one 3 by 3 and one 2 by 2. Okay, pause the video and give it a go. Okay, so we work out the first one. We have 4 times minus 8 minus 10. Subtract 0, well, whatever happens in here gets multiplied times the 0, plus 3 times 10 minus 6. And that works out to minus 24. So be careful with your signs. It gets tedious, but you can do it. Okay, next one has more negative signs to trip us up, but it's simpler. So we have minus 5 minus negative 27, so we get 22. Okay, not too bad. Alright, so the next thing we're going to talk about is working with vectors in matrix form. Again, I'm assuming that you are all very familiar with vectors and how to shift between talking about x and y components and the magnitude and direction of the vector. In my introductory classes, I typically use the magnitude and direction, and I talk about components, and I use the I hat, j hat, k hat component form. But now we need to talk about how we can work with these in matrices, because matrices are going to give us a way to manipulate vectors. And we'll talk about more of that next week. So just to review, when I talk about component notation, which I also use a fair amount, what I mean is you have a vector written like this. So Vx is the x component, Vy is the y component, Vz is the z component. And x hat, y hat, and z hat are the unit vectors. So x hat is a vector of length 1 that points in the x direction. Y hat is a vector of length 1 that points in the positive y direction, and so on. Sometimes a lot of books use I hat, j hat, k hat instead. I personally prefer x hat, y hat, z hat. It's really just personal choice. So we can write a vector as either a column matrix or a row matrix, and which one you choose depends on what you are doing. So when you write a vector as a column matrix, you write the x component, y component, and z component like this. When you're doing a row matrix, you write the x component, y component, and z component like this. So let's say you wanted to add 2 vectors, and you had them in component form. We're just going to connect component form for a little bit so that we're connected to something that's probably a little bit more familiar to you. And let me know how you use vectors in your classes. I'm interested to know. Okay, I'm going to add these as column matrices. Okay, so this is not hard. I'm not going to give you practice this one because I'm assuming it's easy for you. Now let's talk about multiplying vectors. And the first way I'm going to talk about multiplying vectors is the dot product. Let me know if you've used the dot product much at all. I think it's going to look familiar to you even if you don't know the word. For example, work is the dot product of force times distance traveled or displacement. So if I'm taking the dot product of two vectors and I'm doing it in magnitude and direction form, then I would do AB cosine theta. So that's how you end up with FD cosine theta. And this isn't the only thing in physics with a dot product, obviously. So if you see something in your formulas in your classes that looks like this, it's probably because it's a dot product. So let's talk about the physical meaning of this for a couple more minutes. So if this is our vector A and this is our vector B, this is the angle between them. Right, so that's this picture that you know how to use this formula. The length of A times the length of B times the cosine of the angle between them. The physical meaning of this is it's the magnitude of B times the magnitude of the projection of A onto B, or vice versa. And when you're doing vector multiplication like this, it really just looks like basic matrix multiplication. So I'll just pick an arbitrary example here. Okay, so if we're going to take the dot product of these, we'll write the first one as a row matrix, and we'll write the second one as a column matrix. That way the sizes will work out. So this gives us 1 times 2 plus 5 times 3 plus 2 times minus 4. Gives us 9. The dot product is also called the scalar product because the answer you get is just a number. And please always remember that you're thinking about projections. Like when you teach work, what you're thinking about is the component of the force that's along the direction that you're traveling. So if you understand work like that, then you understand what the dot product means. And another important thing to know about dot products, which we will work with more, is you'll see that if the vectors are perpendicular to each other, the dot product is 0, right? Because then one vector doesn't have a projection onto the other vector. Okay, now let's talk about the cross product. So the cross product you might recognize from torque, or you might recognize from E&M. So when you take a cross product and you're talking about them in this form, you're looking at their magnitudes and the angle between them. The magnitude of the cross product is A times B times sine theta. So it tells you, so you should recognize this. And then the direction you have to determine with the right-hand rule, because the cross product is a vector. So basically the cross product is the source of the right-hand rules in physics. So there's lots of different ways of doing the right-hand rule. Have your own version of doing the right-hand rule. Please share in the problem-solving discussion how you do it. Okay, so what is the physical meaning of the cross product? Well, you know the answer to that when you're talking about torque and force of a magnetic field on a charge. But another thing that it means is that the magnitude of the cross product actually gives you the area of this parallelogram, which is kind of cool. But I never had much occasion to think about it that way. Let me know if that gives you some insight. Okay, so the way we calculate the cross product, we have to use the determinant. This is why I said the determinant is useful for talking about vectors. So we're going to use the same two vectors we did a second ago, but since it's on the previous page, I will write them down again. So we're going to take the cross product. So we write the determinant, and what we put in the top row is the unit vectors. In the second row, we write A as a row matrix. In the third row, we write B as a row matrix. And then we calculate the determinant. So we have x hat times minus 20 minus 6. We have minus y hat. Don't forget this one's a minus sign. And we have minus 4 minus 4. Then we have plus z hat. And we have 3 minus 10. So we end up with minus 26x hat plus 8y hat minus 7z hat. And another important fact to know about the cross product is if your two vectors are parallel to each other, then the cross product is 0, because then the parallelogram wouldn't have any area. Okay, and the coolest thing I think about the cross product is that it tells you where the right-hand rule comes from. I'm going to give you two vectors, and I want you to calculate their dot product and then calculate their cross product. And I hope you're getting comfortable with moving back and forth between component form and matrix form. Really, I don't use magnitude and angle very much. It's useful for conceptualizing, but it's harder to work with. So I want you to calculate the dot product of these two vectors, and I want you to calculate the cross product of these two vectors. Alright, pause the video and try it out. Alright, let's work that out. So we have minus 1, 1, 5 times 4, 0, 7. Notice the y hat isn't written out. That means it's 0. Alright, so this gives us minus 4 plus 35. So the answer is 31. It's a scalar. Okay, cross product. Don't forget about your 0. Okay, so if we work this out, so we end up with 7x hat plus 27y hat. Be careful with your signs. Minus 4z hat. So you can write your answer like this, or you can write it as a row vector, or you can write it as a column vector. Depends on what you're going to do with this vector when you're done. Okay, let me know if that makes sense. That's all we're going to do with linear algebra and vectors this week. Next week, we're going to look at some very important topics, how we can represent transformations with matrices, and we're also going to look at eigenvalues and eigenvectors, which are extremely important. Okay, let me know if you have any questions or comments in the problem-solving discussion. Okay, see you next week.